Hello, can you hear me? Udar sir? हेलो 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 माइक टेस्टिंग 1 2 3 और उधर से कुछ बोल
हेलो 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 हेलो। हम मेरी नहीं आ रही ना।
तेरी आ रही है।
तो फिर इधर इसको
हेलो।
चेंजेस कर रही है। हेलो नहीं।
हेलो हेलो हेलो
हेलो हेलो। अरे ये स्पीकर कनेक्टेड नहीं है।
हेलो हाँ
हाँ, पर मैं यहाँ से जो बोल रहा हूँ वो यहाँ से नहीं आ रहा।
देखो तुम्हारा पार्टी आ रही नहीं आ रही बस
नहीं।
तेरे से भी नहीं आ रही
दादा दादा
हेलो
इथंच
हेलो हेलो
इथंच
हेलो हेलो हेलो
आ रही क्या
मतलब आम्ही ऑनलाईन जॉईन केलंय. इथला आवाज स्पीकर मधून
हेलो 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 इधर से आ रहे हैं हेलो 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 हेलो
तेरे काम कर रहा था यार मेरे किसका काम
हेलो 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 हेलो
इसमें आ रहा है
इधर आ रहा है.
मेन स्पीकर पे आ रहा था ना थोड़ी देर पे हाँ अभी आ रहा है तो हेलो 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 हेलो
Mic. Hello, mic testing. 1, 2, 3. Hello, mic check. 1, 2, 3.
हेलो 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 हेलो
Hello, mic check. 1, 2, 3, 4. Hello, mic check. 1, 2, 3, 4. Hello, mic testing. 1, 2, 3. आप बाहर जाके अभी बात कीजिए, फिर आपका इको नहीं।
हेलो 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 हेलो
Hello, check,
हेलो
test,
हेलो
test,
हेलो हेलो
hello, hello,
चेक चेक
check.
चेक
बाहेर गेलते. हो. हां, हां.
हेलो 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 माइक चेक माइक चेक माइक चेक हेलो 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 माइक चेक माइक चेक माइक चेक हेलो 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 माइक चेक माइक चेक माइक चेक हेलो 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 माइक चेक माइक चेक माइक चेक हेलो 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 माइक चेक माइक चेक माइक चेक
काढायची का परत?
हेलो 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 माइक चेक माइक चेक
हेलो माइक चेक. हेलो, हेलो. Hello, 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 hello. Hello, hello. बता रहे? Hello, 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 hello. पीछे जाएगा सर. All good. Audio is good. Good, good, good. Yes. Hello, hello. Hello. Hello, 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 hello.
Mic check, mic check.
1, 2, 3, 1, 2, 3. Okay, very good. We turn it off now.
Okay, good morning and welcome to the second day of the conference. So today we start our session with an invited talk by Professor Moshe Vardi. So it's my great pleasure to introduce Professor Moshe Vardi to all of you. He really doesn't need much of an introduction. Uh, uh, Professor Vardi is a university professor and a George Distinguished Service Professor of Computational Engineering at Rice University. He works at the interface of mathematical logic and computation, and he has worked in diverse areas, including database theory, hardware-software design, formal verification, multi-agent systems, constraint satisfaction, finite model theory, and there are several results that are known by his name in all of these areas. He is the recipient of several awards, it's a very long list, including the Gödel Prize, the ACM Kanellakis Award, the ACM Sigmod Cord Award, the Knuth Prize, the IEEE Computer Society Good Award, the EATCS Distinguished Achievements Award, and so on. He is the author or co-author of more than 750 papers and has also authored multiple books. He's a fellow of several societies. He's a Guggenheim Fellow. And he also holds membership of some of the topmost scientific societies in the world, including the US National Academy of Engineering, National Academy of Science, the Royal Society of London. He holds 9 honorary titles, and a lot of us may have read his column in Communications of the ACM. He's a senior editor of Communications of the ACM. So with that brief introduction, I'd like to welcome Professor Vardi for today's keynote talk.
The mic. Yeah, I have the mic. Well, good morning, everyone. And I thank the program committee for inviting me, and thank you, Supratik, for this very kind introduction. And I'm going to try to take you this morning a 50-year-long journey. And I'll try to make sense of what is this concept of logical algorithmics. How do we go from relational queries to automated reasoning? So let me just remind you on basic first-order logic. When there is important syntactical distinction between formulas and sentences. So a formula can have three variables. Okay. So in this formula, you see x is free, and the formula says that there exist two variables, y and z, that are different on each other, and each one is a neighbor of x. So it said that the node x has two neighbors, at least two neighbors. And you say, is this formula true for a given graph? Well, it does make sense because x is free. So what is x? It's like asking, is x equal to? You have to bind x. And usually we use variable assignments, alpha, to bind the free variables. Now here, in the second sentence, there are no free variable. It says for every node, there's at least two distinct variables. So this is a sentence, and it's either true or false in a given graph. Is it true that every node has at least two distinct neighbors or not? Now, if you take a standard course in first-order logic, then formulas are some kind of syntactical nuisance that we have in order to get to the promised land of sentences. Sentences makes assertion about structures. So in particular, if you have a sentence psi, then we can define model of psi, which are all the graph. I'll focus on graph here, but could be arbitrary structures, all the graphs that satisfy psi. And so now we can look at the modeling power of first-order logic. So you can think of model theory, the meta theory of mathematical modeling. We want to describe class of structures, and we're going to use logic to describe classes of structures. And I said, formulas are kind of a nuisance to get two sentences. But then in 1970, Ted Codd said, no. Formulas are interesting on their own sake because they define queries. So what is a query? If you take a formula phi and you apply it to a graph G, you look at all the assignment that will satisfy the formula and return all the tuples of assignment to the free variables. So if I go back to my formula that says x has two distinct neighbors, as a query, it says, give me all the nodes that have at least two distinct neighbors. And in that case, now we see the sentence, because it has no free variables, it's a Boolean query. It's a query, but it just returns 0 or 1, yes or no. So this is really an important idea by Ted Codd. And in his paper, he actually had two very important ideas. One is a traditional notion of a table we all use to describe data. Half of the paper here at SAT will have table. These are really mathematical relations. Relation is a set of tuples. So a table is just a relation. That's why it's called, in fact, some people used to call in the old days, there was some name was tabular databases rather than relational databases. And formulas are query. And now we can describe, instead of writing imperative queries, here is how you compute. Go over all the nodes. For each node, check whether it has at least two distinct variables. If yes, return it. You can write an imperative program. Now you write a declarative program. And out of this came SQL, which was a huge success as a declarative. It was the first declarative and the most successful declarative programming language. What I want to focus here on another one that kind of gets lost sometimes in this discussion, which is what Ted Codd introduced, was a very intimate connection between logic and algorithms. And this let's take a look first of all at algorithmic problem in first-order logic. So this is a problem you all heard about, the satisfiability problem. Given the first-order formula, is there a graph G and assignment alpha such that the sentence will be true? This is a satisfiability problem. Dually, is it always true? That's the validity problem. And you should all know that this is undecidable. This is the classical result by Church and Turing, and for finite graphs by Trachtenbrot in 1950. Church and Turing did it for arbitrary structures, finite structures, Trachtenbrot. But there is a simpler problem, which is, given a formula, a graph, and a binding, is it true? Does the graph satisfy the formula under this binding? Now, for finite structure, it's trivially decidable. Why? Because every quantifier is just loop over all the elements. So you can just write a big nested loop going over all the quantifiers and check for each assignment. For each assignment, all the variable, check it. And so it is trivially decidable because it's a finite relation. And in fact, this result is so trivial, you'll never find it in a logic textbook. You'll never find a theorem that says that truth evaluation problem or model checking, if you want, for finite graphs, finite structures is decidable. You ask a logician, they say, yeah, of course it's decidable. Who would write such a theorem? But I would argue it's a very, very important theorem. Now, why is it important? What's happening? Okay, I don't have the magic touch. Okay. So, okay. So this connection gives rise to what I call logical algorithmics. So think typically, you take an algorithm course or you teach an algorithm course and you find a chapter on, who knows, perfect matching, okay? So there will be some mathematical definition of perfect matching. And then we develop an algorithm for perfect matching. And this is the standard. We describe a problem in words, then maybe we write it formally exactly what it means, and then we come and develop an algorithm. But now we have a new way to develop algorithms. Describe the property in a logic. I'm talking about properties of graph. Describe the property in a logic. Now think of the logic as a query. Think of this as a query and just run the query evaluation algorithm. Remember that the query on sentences return yes, no. So just run your query evaluation algorithm for this particular logic. I mean, we saw that for first order logic, there is a very naive algorithm. They just try all possibilities. Whenever they quantify, it will check all possibilities. So evaluate the query, and it will return 1, then it means that the property holds. So if for this logic, you already developed a query evaluation algorithm, you don't need to develop new algorithm as long as you express your property in this logic. So this logic in general can be viewed now as a declarative programming language. Describe the property and just run the standard algorithm for this logic. First order logic, we have one. I'll mention some other logics. And it will give you an answer. No need to sit down and say, oh, how do I do this particular problem? How do I solve another problem? Just describe it. This is the whole idea of declarative programming. Don't tell the computer the how. Tell the computer what do you want, and let the compiler figure it out. So this is the idea of logical algorithmics. Now, as soon as you start looking at that, you say, oh, good, let's look at various graph theoretic properties. Let's say I'm interested in three-colorability. Can I express it in first order logic? The answer is no. And if you think intuitively, if you have the color, checking that there are no monochromatic edge, that is a first order property, but you have to say there exists a coloring of the graph. So this is actually will be a quantifier, second order quantifier, that when you quantify over the color classes, you say there exists a set of node for red, a set of node for green, a set of node for blue, etc. So for three colorability, you need existential second order logic. So in 1974, so exactly 50 years ago, Ron Fagin looked at the expressive power of this logic. What kind of queries can it express? And it proved an absolutely beautiful theorem that said it's expressed exactly NP. So if we essential second order, it is an NP, you have to guess the relations, because there are exponentially many relations. You cannot enumerate them. You guess the relation, then you evaluate the first order query. This is NP, but vice versa. For every NP query, there is a way to go from Turing machines to express the query in essential second order logic. And it's a beautiful result because when I talk about this kind of this notion of queries, there's no computation here. It's just logic. There is polynomial time here. There's no polynomial time here explicitly. You have to think hard to see why is it polynomial time. And nevertheless, you have this equivalence. And that actually gave rise to a theory, became active topic of research called descriptive complexity theory, which looks at the complexity of problems, not in terms of, I have an algorithm, how long does it run, but what does it take? How much syntactical resources is needed to describe the problem? What kind of logic do I need? How many quantifiers do I need? What is the length of the formula? For example, one thing that follows from Fagin's theorem was that if you look at full first order logic, it's exactly the polynomial hierarchy. And Neil Immerman really became kind of the high priest of this research direction, exploring the deep connection between computational complexity and their descriptive complexity, and he published a book about this, beautiful book, in 1999. So this is one thing we got out of this perspective of logical algorithmic. We got a new type of complexity theory. Now let's go back, look at this idea that we can check satisfaction by running the Cour evaluation algorithm. So in 1982, a young postdoc asked, what is the complexity of this Cour evaluation algorithm? Well, it's an algorithm. It's what we call the meta algorithm. It has its own complexity. What is the complexity? Then you realize, well, first of all, it will depend on the logic. We saw so far two logic, first order logic and essential second order. But also, strangely, this algorithm has two types of inputs, the query and the database or the graph. So how do we take these two different inputs into consideration? And in fact, if you look at Fagin's theorem, it said that for every fixed ESO query, this is going to be in NP. What happens if it's not fixed? What happens if you say, no, the query is part of the input? I want to know the complexity also relative to the query. So that's not answered by Fagin's theorem. So let's first look at the question, what logic? We saw already two logic, first order logic and second order logic. Already in the 70s, people realized it's not enough. Essential second order is very powerful, does all of NP. But first order logic is too weak. In particular, it cannot express a very, very useful query, which is just connectivity, graph reachability. I want to know, can I get from point X to point Y with using a path of arbitrary length? If it's any path of fixed length, you can use first order logic. But if you want to know a path of arbitrary length, you cannot use it first order logic. This is a theorem. So Chandra and RL proposed in 1980 a new logic called fixed point logic, which is first order logic with induction. So you essentially iterate a first order query until convergence. This is fixed point logic. And in expressive power, it sits nicely between first order logic and essential second order logic. So we are going to consider all three logics. There are other logic one could consider, but this gives us the basic three logic we're going to consider. But now let's look at the issue of how to measure complexity. And here we need a new perspective. And that perspective today is called, not at the time, the term didn't exist, but today it's called multivariate complexity theory. So what is multivariate complexity theory? So complexity theory looked at scaling behavior of algorithm. What happens as the inputs get larger and larger? How does the runtime or the space usage scale as a function of the length of the input? Now, in our case, if we took the standard notion, the length of the input will be the size of the query plus the size of the data. But if you think in practical setting, there's a huge mismatch. How big is the query? Who knows? But yeah, big. 100. How big is the data? Terabyte. So now we're looking at input size will be 1 billion plus 100. So you say, well, the 100 is negligible. Well, no, it's the query. And in fact, what do you think will be more challenging? To double the size of the data or to double the size of the query? So the answer for that is that we need to study the role of both inputs. That's why it's called multivariate complexity theory, and that's not reflected in standard complexity theory. And in some sense, if you think about parameterized complexity theory, or you have a parameter, it's also an instance of multivariate complexity theory. But parameterized, we'll see parameterized complexity theory came a bit later. So the idea is we want to separate the influence of the query and the influence of the data. How do we do that? Reductionism. We want to study the influence of the query. We fix the size of the data. We take a fixed database and we just vary the query. We want to study the influence of the data. We fix the query and we vary the data. And it turns out this actually has real life motivation, because there are scenarios where, here is a scenario, kind of demographic queries. United States, by the Constitution, every 10 years, we do a census. There is a census bureau, there is a government body. Every 10 years, it counts all the people and collects lots of data about them. And it gives rise to the allocation of congressional seats. So it's actually of tremendous consequence, but also they got a lot of demographic data. And demographer will spend the next 10 years running queries against fixed data. For 10 years, the data will be fixed. On the other hand, think of yourself now as a quant on Wall Street, where we do price arbitrage. What happens? You may have a fixed query, but you run the query every minute to see, okay, do I have a trading opportunity? Is there a mismatch between the New York Stock Exchange and the Chicago Board of Trade? And in each case, I can pounce and issue a very fast sell or buy order. So in this case, we have fixed query, but varying data. So this gives rise to three ways of looking at complexity. One will be fix the data. Here we have fixed B, and we vary the query. We want to know, given me find all the queries that evaluates to 1. Other one is we call data complexity. Fix a query, vary the data, and tell us when it's going to be 1. Or you can look at the combined complexity, where really both are given to you. Okay? This is the tale of three complexity. And what did we learn about them? And this is what I did in 1982. Turns out, exponential gap between them. You look at first order logic, we can evaluate first order logic. If you look at the naive algorithm that enumerate all elements, whenever you see a quantifier, you enumerate all elements. To enumerate all elements, you only need log space, because you just go enumerate elements by one by one. You never need to store all the elements, just the number of depending how many quantifiers you have, exists X for all Y, exists Z, you have to enumerate triples of elements. So it's log space, data complexity, but expression complexity, it is piecewise complete. In fact, QBF can be viewed as a query over a very, very simple database with 2 elements and relation that is true for one element and not true for the other element. So this is really, QBF is a special case of this. So we have exponential gap. For fixed point queries, data complexity, the answer is you evaluate a query, you evaluate first order query, and you iterate it until convergence, because you have because here for data complexity, the query is fixed. There is a fixed arity, so the number of tuples is polynomial, so it will converge in polynomial time. But when you go to expression complexity, it's now exponential time, and now you have completeness here. For log space, it's hard to prove completeness because the reductions are log space, so it's hard to prove completeness. But everything else we have completeness, and this was Fagin's theorem when the query are fixed. But you go to expression complexity, it's become next time. So what does it tell you? That the queries, even though they're small, they count much more in sum. The data is flat. The data is kind of dumb. The queries is where they're smart. So doubling the size of the query will have huge impact. That's why we do query optimization. Because if you just take query and you try naively to evaluate it, it may be hard. So query optimization is, how do I take that query and rewrite it so it'll be easier to evaluate? You don't hear about data optimization. You hear about query optimization. And this distinction turns out has broad applicability in many contexts in AI now. You realize in some there is something called the query, something called the data. And I'll come back and we'll see a scenario or it's not obvious what is data, what is the query, and I'll show you. You can look at it using the same lens. And a few years later, by 1981, parameterized complexity as a special case of multivariate complexity came out. And today, many people prefer the term multivariate complexity theory because it's broader than parameterized complexity theory. So let's look at this, again, let's look at this little table. So Feigl's theorem said that this result here is tight, that existential second order equals NP. So the question that you ask yourself, okay, is FP in the same sense fully characterized polynomial time? And the answer is no. There are easy queries, for example, asking, does the graph have an even number of nodes? You cannot evaluate it using clearly polynomial time. You cannot evaluate using fixed point logic. In 1982, Immerman and myself independently proved that over ordered structures, you get this equality, a fixed point equal polynomial time. And you need order because Turing machines have order. It's the tape. The tape is an order. You go from left to right. If you want to put a graph on a tape, you have to choose an order to do it. We usually don't talk about it, but if you want to put a graph on a tape, you have to decide how to put the graph on a tape. That creates order. But if you take away more abstract logical notion, it's hard to do it without order. And this is by now, a question has been open now for decades. Is there a logic that will characterize P time in general on unordered structures? Still very much an open question. Subject of research now for over 40 years. Now, I said that this data versus expression complexity has a broad applicability. Let's take a problem that's closer to the subject matter of this conference, consent satisfaction. So SAT is a special case of consent satisfaction. In general, what is consent satisfaction? You have a set of variables. In SAT, there are Boolean variables. You have a set of values. In SAT, it's just the Boolean values, but in general, a set of values. And you have a set of constraints. What is a constraint? A constraint is a tuple of variables in a relation of the same arity. A tuple of variables, relation of the same arity. And what is a solution? A solution has to be an assignment to the variable. You assign values to the variable. And what you want is to look at each constraint, the assignment to the tuple has to be in this relation. And we'll see in a few minutes how, for example, SAT is a special case of this. So this is very, very general problem of major interest in computer science and artificial intelligence. There is a conference, consensus programming, that looks at this problem. General problem is, do we have a global assignment to all the variables such that all the local constraints are satisfied? So huge research topic. SAT is in some sense a special case of this larger research topic. And this problem in general has application all over the place. So you find, in programming languages, in AI, in a whole bunch of different area, you look, oh, it's a CSP. Here is another problem that is, many of you maybe not even be familiar with it. Given to relational structure or the same vocabulary, the vocabulary is the names and arity of relations. You want to define a homomorphism between them. So you're given two structures. So here you see they have the same number of relations, and each matching Ri here and Ri there will be of the same arity. That's important. A homomorphism is a mapping of the domain A to B, such that take every tuple, if it's in the relation R sub I in A, then its image will be in the relation R sub I in the structure B. So in the case, if you think of graph homomorphism, you map one graph into another graph, such that every edge in the left graph maps to an edge on the right graph. In particular, if you take a graph and you try to map it to K3, which is the three click, the three complete graph, the three node complete graph, you realize this is exactly three coloring. So three coloring is an instance of CSP. When we use on the right, we use the triangle. And this, on the face of this, CSP and homomorphism look like very different problems. Now, again, you can find homomorphism is of broad applicability. If you want to check, does the graph have K click? You're asking, is there homomorphism from K sub K to the graph? That is a Hamiltonian cycle. You want to map a cycle of appropriate length to the graph without collapsing nodes, subgraph isomorphism, and even ST connectivity. Now, in 1993, Thomas Feder and I declared the two problems to be the same. Now, what does it mean that two problems are the same? On one hand, they are both NP-complete. So they're all polynomially reducible to each other. All NP-complete problems are polynomially reducible to each other, but we don't say they're the same problem. Our argument was that the reduction in both directions are so trivial that just amount to syntactical reformatting. Okay? Imagine that I tell you, okay, I'm going to take the syntax of first order logic, I'll define a new logic, we'll call it mirror logic, in which you write the sentences in Hebrew from right to left. You say, okay, it's the same thing. You didn't change anything, you just flip the syntax. And that's the argument here. The syntax, if you dig into it, the syntax, the reductions are so trivial that it just amounts to syntactical reformatting, so it's the same problem. Now, it was interesting because people have studied in different contexts and did not realize the connection. For example, if you go to, there was a very fundamental book in complexity theory, Gary and Johnson, 1979, and homomorphism was there because it's a kind of a mathematical notion. CSP is AI, CSP was not there, okay? But it's the same problem. Now, let's go back to the multivariate complexity theory lens. So if you can look at so uniform CSP, we're looking, given two graphs, is there homomorphism from A to B? And as you may know, NP-complete theorem started in the West with two papers. First, Cook defined a concept and showed the satisfiability is NP-complete. And then Descartes showed that there are many other problems are NP-complete. The Soviet Union, this was done independently about the same time by Leonid Levin. Both results essentially in one paper. In particular, he proved that homomorphism is NP-complete, which you saw we can encode three colorability. So yes, obvious. Now let's go back to the multivariate complexity view. Now we can think of A as the query and B as the data. You're asking, can I find a copy of A inside B? And so now we can look at it from this multivariate complexity theory perspective. So that what we call the uniform problem is really combined complexity. You're given both the query and the data as input, and you're asking your query. So that's what we call before uniform combined complexity. But now we can look at query complexity, expression complexity, and data complexity. So one thing we could do, we can fix the query. So we fix the graph A, and now we're looking for all the graph B, such as A homomorphically maps to B. That will be the data complexity view because we fixed the query. And it turned out, again, you just have to enumerate all possibilities. It's a fixed query, so it's in log space. So you check all possible assignments, all possible mappings, but because it's a fixed query, you can do it in log space. If you have k variables on the left, it will be k log n, and k is fixed. So that's in log space. Or what you can do is you can fix the data. You could fix the target graph and vary the query. Now you find what is the complexity? It depends on the target graph. So let's think of graph, and what happens if the graph on the right is K2? Then this is two colorability, it's polynomial time. But if the graph is K3, this is three colorability, so it's NP-complete. So the answer is, if we're going to do the expression complexity, it will fix the data. It will depend on the data. So in 1993, Thomas Feder and I embarked on a research program. So we see sometimes it is tractable. Sorry, sometimes it is tractable. I cannot go back. Okay, can I go back? Okay. No, I cannot go back. Okay, I can go back. So sometimes it's tractable, sometimes it is not. We want to know when is it tractable, when is it not tractable. In particular, we made a conjecture became known as a dichotomy conjecture. The conjecture was, depending on the target graph, it's either going to be in P or NP complete. And this is a dichotomy because in general, you should know that if P is different than NP, then there are problems that are called in-between problems. The problems that are not in polynomial time, but not NP complete. But in this case, the conjecture was it's a dichotomy. It's either NP or NP complete. So that was the conjecture that went back to 1993. Now, to make progress on this, there is a concept that we're going to use, which is product of graph. So given two graphs, you define the product. We're taking the product of the sets of nodes. And over this set of pairs, there is an edge between two pairs if the corresponding edges exist in underlying graphs. There will be an edge from u prime to v prime in the product graph, and there was an edge between u and v in E1, and an edge between u prime v prime in E2. You can take this concept also to general relational structure in general, but we'll just stick to graphs for now. So this is the concept of graph product. So now there is a concept that was introduced originally in universal algebra, which is a branch of model theory, which was very popular in the Soviet Union. We'll see this is important. So there's a concept of polymorphism. What is a polymorphism? You're given a relational structure. A polymorphism is a homomorphism from a power of that structure to the original structure. So it's a homomorphism from take the graph, take this graph product with itself, k times, and then you map it. If you can have homomorphism to original graph, then this is a k polymorphism. And we argued in 93, we actually did not know the term polymorphism, but we defined the notion. And we argue that these are important objects. And we demonstrated by an interesting, surprising theorem. So let's define k unanimity for a k-array problem for a function if k minus 1 of the inputs equal a, then the output should be a. So it's called near unanimity. It doesn't require that all the inputs agree. If k minus 1 agree on the value, that should be the output. There's one outlier, just ignore it. For example, 3 majority, if you have a majority between 3 elements, that's an example of near unanimity because you have enough that you have 2 that agree, you can ignore the third value. And the theorem that we proved was that if you have a structure B and the set of polymorphism contains unanimity function, then CSP, when B is the target, is in P type. Remember, we're looking for conditions on B that will tell us when is CSP of B in P time, when is it NP complete. There was a conjecture, it's NP complete. As I said, polymorphism are studied in universal algebra, and Peter Gibbons from Oxford took this concept. I mean, we were not familiar at the time with universal algebra. Pete Gibbons was, and he, together with collaborator, was able to prove that if you have 2 structures and the set of polymorphism is the same, then the 2 CSP problems will be polynomially equivalent. And this means that the set of polymorphism of a structure of a graph B characterizes fully the complexity of CSB of B. And that means if we want to resolve the conjecture and classify when is CSP tractable or not, it's all about studying polymorphisms. And it became very clear that what you need is people who expertise in universal algebra. And P. Gibbons was able to bring several young Russians to work with him on this. And just to understand, in all of mathematics, you have let's say this room is all of mathematics. Here in the corner is discrete mathematics. And then let's suppose that the whole room is discrete mathematics. Here in the corner, it will be mathematical logic. Let's imagine the whole room is mathematical logic. Here in the corner is universal algebra. So this was a tiny, tiny, obscure corner of mathematics. And suddenly they have been discovered. Computer science wants them. So there was a celebration among universal algebraists. Wow, people are interested in us. Look at us. We're important. I mean, before that, if a plane there were about, I don't know, 50 universal algebraists in the world. If the plane carrying them to conference crashed, no one would notice. Suddenly, they are very important. And several years of research remember, we started in the 90s. By 2017, finally, two Russians using universal algebra was able to prove the dichotomy theorem using heavy universal algebra. In fact, many people like me, by the mid-90s, we said universal algebra, forget it. We're not going to dive deep universal algebra. We left universal algebra to do it, and they were able to deliver. It took them more than 20 years, but they were able to prove the dichotomy theorem and give us the classification. It is decidable, given a target graph, B, whether CSB of B is tractable or not. Now, I want to generalize the concept of, before we saw uniform CSP and non-uniform CSP. I want to find something in the middle. Something in the middle is going to be semi-uniform. In semi-uniform, instead of having a fixed query, we have a class of query. So the data is completely variable, but we have a fixed class of query. And we want to know, can we find characterization for classes of queries that will be tractable? So each single query, we saw it's in log space. But are there large classes of queries that are going to be tractable? And we were able to do it in 2002 together with Dalmau and Kolaitis. So the concept of a core of a graph. A core of a graph is a minimal homomorphic substructure. So it's a substructure, subgraph, such that the whole graph can map homomorphically to it. And because it's minimal, all such subgraphs are going to be isomorphic to each other. That's easy exercise. So this is the core of a graph. We're interested with a C sub k will be graphs whose core has 3 widths at most k. I'll come back and be more precise about 3 widths in a few minutes. But it's a fundamental notion in graph theory. So these are going to be C sub k are graph with bounded 3 widths core. And we prove that if the query here is in C sub k, then this is tractable. For all of the query, there is an algorithm for everything in C sub k. K, of course, will affect the complexity, but for a fixed k, this is tractable. And a few years later, Martin Groy was able to show under complex theoretic assumption for parameterized complex theory that this is if and only if. So if you want to find a class of graphs for which this is tractable, they have to have bounded 3 widths core. Now, finding the core it's not easy to find the core. You have to guess the core, check it. It's not easy to construct the core. So this is, some people we call it island of tractability, because you know it's tractable, but you don't know how to find that island. So it's not a very useful result. So to make it useful, let's go back to relational complexity theory. So in 1995, I showed that I asked the question, why we saw that the express complexity is very high. Why is it so high? So let's take, for example, just evaluating join. Well, it's a bit analogous to take when I was in 4th grade, an 8th grader came to me and says, I hear you're good in math. I said, yeah, I'm pretty good. He said, okay, here's exercise for you. And I start computing, left to right, left to right, left to right, left to right. Oops, I realized that I've been had. So what happened? You have a large join, for example. You start doing the join. The outcome can be empty. But in the middle, you can have very large joins. So can we we would like to formalize when do we have small intermediate results? And the answer is variable confined query. let's look at the following. Suppose I want to, Mike, we lost the mic? Okay. Suppose we have, okay? Suppose we have to do the following. Take a join of two relations, R1 and R2. They're both ternary relations, and the third column of one has to be equal to the first column of one, and then you project on 1 and 6. So the intermediate relation here, at the end you get binary relation, but the intermediate relation will be 6R relation, which can be large. But when you look at it, you realize that the middle column of R1 and R2 are not relevant here. So you can start by projecting them out. And then if you do that, if you're smart about that, then you're going to get only a 4R relation in the intermediate relation. So this idea of this we call projection pushing. Project eagerly. Join lazily, project eagerly. This turned out to be equivalent to reusing variable in first order logic, and to bound the width is equivalent to bounding the number of variables. So variable confined queries is a logic where you bound the number of queries. If you have a logic L, like first order logic, L sub k would be you only have access to k variable. So we can take a standard query, like this is there a path of length 2? You can write it using 3 variables, either x, y, and z, such that r of x, y, r, y, z. But if you're clever, you can reuse variable and write it using 2 variables. So imagine that I give you the syntax that says, this is a finite planet. Okay, not usually if a textbook says you have infinitely many variables. Wait a minute, this is a finite planet. Where do you get infinitely many variables? It costs ink to write the subscripts. So we give you only finitely many variables. So it turns out that if you bound the number of variables, expression complexity comes down. So for first order logic, it goes from p space to p time. For fp, from x prime to p time. From next prime to np. So except for the beginning, you see it goes down exponentially. In fact, we close the gap between data complexity and expression complexity by bounding the number of variables. So the fact that we can kind of reduce the complexity exponentially, almost in general, by bounding the number of variables, suggests that this is a good optimization strategy. Given a query in first order logic, find the minimal number of variables in which you can rewrite it to be equivalent query. That's the ultimate optimization, except it's undecidable. First order logic, everything is undecidable. So it's a nice notion, but not useful. But maybe there's another class of query which is important, in which it is decidable. And this class of query is going to be conjunctive queries. And conjunctive queries correspond to first order logic with just conjunction and essential quantifier. No negation, no disjunction, no universal quantifier. And they correspond to SQL queries that we use essentially projection and join. So these are very, very practical queries. And in 1998, Colois and I declared that conjunctive query evaluation is essentially CSP. And again, what does it mean the same? The reductions are so trivial that we can view them as the same problem. So we're back to CSP. Now, it was well known that to evaluate conjunctive query, the expression complexity is NP complete. This was, again, you can encode tricolorability. If you look more precisely, the multivariate complexity, you see it is the size of the data, and the exponent is the size of the query. And that's pretty bad to have the query in the exponent. And Yanakakis in 95 pointed out, using the lens of parametric complexity theory, that this says that on the face of it, this is not fixed parameter tractable. Because for this to be fixed parameter tractable, we want to decouple. We don't want exponential in the data and the query. We want it to be some exponential in the query, but then polynomial in the data. That will be fixed parameter tractable. And indeed, in 1997, Papdounis and Yanakakis showed that under complex theoretic assumption, this is not going to happen. Conjunctive queries are not fixed parameter tractable under reasonable complex theoretic assumptions. But now we can ask, can we bound the number of variables for conjunctive queries? Can we look at C sub k, where you are able to rewrite it using only k variables? And then it turns out that if you can write your query using k variables, Then you can evaluate in time, which is linear inside of the query, and polynomial in the side of the data, where k is the degree of the polynomial. But if you fix k now, this will become fixed parameter tractable. So for conjunctive queries, this rewriting does reduce the complexity. It's an effective strategy to reduce the complexity. Again, you can look at the query that I had before using 3 variables, the query that I had 2 variables. This is going to be easier to evaluate. So we're realizing here, the point is the number of variables. That's the critical parameter. And can we now take a conjunctive query and find out what is the smallest number of variables in which you can rewrite this conjunctive query? Remember, for first order logic, this was undecidable. What about conjunctive queries? So let me remind you what is tree width. So you're given a graph and you're asking, how tree-like is it? And the answer was, well, massage it into a tree. So you create, or some people call these potatoes. And inside this potato, you have to include all the edges between the nodes, right? So if I have here, you have to say that there is EG is an edge, so it has to be inside here. EH is an edge. And you're counting the number of nodes in a potato minus 1. In this case, this is the composition of width too. I won't give the formal definition here. I'm sure many of you have seen it. But the idea is it's a parameter characterized how tree-like is the graph. Now you can apply it also to queries. Why? You have a conjunctive queries. The nodes are the variables, and there's an edge between 2 nodes if they appear in an atom of the query. So this is the same way you can define, if you have a CNF formula, you can define the graph of the formula. All the variables are the nodes. There is an edge between two variables if they co-occur in a clause. And the tree width of the query would be tree width of that variable graph. This is called a primary graph. And in 1998, colleagues and I characterized it that Q can be rewritten as a formal definition. There are some rewrite rules. Rewritten is in CK sub K if the tree width is at most K, is less than K. This suggests that bounded tree width conjunctive queries are going to be fixed parameter tractable. So this gives us nominally a strategy for optimizing conjunctive queries. Create a tree decomposition and then use it to evaluate the queries. Well, finding tree width of a graph is by itself NP hard. So not clear exactly how we can use it. But still, there is interest in using it because there is a problem in databases that actually is important, and this is evaluating large joins. Large join will be, suppose you have a join of 50 relations. There are class of problems where you have very large joins. So standard databases, the way data optimization work, they take the query, they formulate what they call query plans. They evaluate the cost of each query plan and then define a good plan. The problem is the bigger the query, the more plans there are. It blows up exponentially. So if you take 50 relations, the search space is going to be unwieldy. So standard query optimization technique will not work. So can we use the structural theory to do that? And together with the student Ben McMahon, we says, well, remember, query evaluation is CSP. Let's borrow heuristics. So we don't know how to compute tree decomposition. But what we showed is that CSP heuristics are heuristic to approximate the tree decomposition without being able to say anything formal how good they are. They're just heuristic. But they are given us a way to minimize the number of variables using this heuristic. And the question was, okay, how good is it going to be? And the answer was, it was fantastic. It gave us, this shows how we start with just standard SQL engine, and then we apply different heuristics, and this is log scale. So we see we get exponential improvement in the performance. And in fact, we had it was an event with the Trice, and there was poster competition, and he had one slide. He said, this was when I ran SQL, this is my algorithm, it's an exponential gap. And he won the best poster award just by showing this improvement. Now, At the time, we couldn't even hope to use 3D composition because it was just beyond reach. But in the meantime, in the past 20 years, the same way that SAT is hard, but we solve SAT. Here's the composition is hard, but there are tools, there are competition. The 3D composers are getting better and better every year. So it's an interesting question. Can we go back to this core optimization and use 3D composition? Now, I've moved away from databases. Also, there are good argument why 3D composition may not be just exactly the right tool for database queries. There's a whole theory of hyper 3D composition that seems more appropriate for query decomposition. But I want to go now back to Boolean CSP. Now we get to Boolean reasoning. So in Boolean CSP, we have clauses. Let's look at 2SAT. In 2SAT, there are 3 possible clauses, right? Both positive, both negative, and mixed. And each one there are 3 truth assignments to each clause. And this is true in general. If you look at 3SAT, I think there are 8 possible clauses, and each one corresponds to a relation of 7 truth assignments that are satisfying. And it is a problem of conjunctive queries because we're trying to, you're given a SAT instance, clauses, you build a relation corresponding to each clause, take the join of all of them. This is exactly the set of satisfying assignments. So satisfiability asks, is the join non-empty? Now you think, okay, let's use joins. The problem is, we know that the outcome of the join is going to be very large. So this is not a practical way to do satisfiability. It's too large. You have the magic touch, I don't. Okay. So we're going to try to use it, first of all, address the issue in 2 ways. First of all, we're not going to represent relation explicitly. We're going to use BDDs to represent set of truth assignments. So BDDs gives us a compact way, compact in a good, not always, in the worst it's going to be exponential, but many cases BDD gives us a compact way of representing, and we're able to manipulate a set of truth assignments. So you can imagine this join. I do it not on relations, explicit relation, but on symbolic relations using BDDs and then taking the product of this BDD, the conjunction of these BDDs. I'm assuming everybody knows about BDD, so I will not use it here. And in 2005, Gokchan Pan and I tried to use BDDs and CSP heuristics for doing SAT solving. The answer was, in general, it was not, already then it was not competitive against CDCL solvers, but there were cases, there were there were formulas that were hard for SAT solver because they were hard for resolutions. You take, for example, PHP, and it's hard for resolution, but BDDs can do it efficiently. So it was still an interesting approach, but if you're looking for general purpose solvers, it was not competitive. But more recently, I've been looking at quantitative Boolean reasoning, in which we look at model counting, SharpSAT, which is sharply complete, and in fact, weighted model counting, where each literal has a weight, and we take, for each assignment, we take the product of the weights, and then we sum the product of the assignments, and that has a huge application in probabilistic reasoning. So the question is, can we now take, again, this conjunctive queries approach and apply it to weighted model counting, for example? So now we need to go from BDDs to binary decision diagram or Boolean decision diagram to algebraic decision diagram, where the leaves you can have numbers. Okay, you can have floating point numbers. And so this is the way to represent what we call pseudo Boolean functions. And it shares a lot of the same advantages of BDDs. You get canonicity, you can do sum and product of ADDs, and the BDD packages also support ADDs. So we don't have to do something new here. We can just use existing package. So how will we do weighted model counting with ADDs? We will start by constructing the BDD for the formula. We will construct the BDD for the formula. And go back, okay. Okay. So we'll start with the BDD. We'll add the weights. We'll get an ADD. The problem is, again, if we do this, it will blow up. If you try to do it for the whole formula, it's going to blow up. So instead, we said in 2020, let's use the same CSP heuristic that Pan and I used in 2004. Let's use it here to minimize the size of intermediate results, minimize the number of variables. And we built a solver called ADDMC. And in 2020, it tied for the first place in the weighted track. And you can look at the performance here. And the way, it's hard to find in this area, it's very competitive. It's hard to find an algorithm that will beat all algorithms. So instead, you're looking at the portfolio and you're asking, does it improve the portfolio? So here we had a whole bunch of solvers. And then we added ADDMC. And the green line was the virtual best solver, the best running time of all solver before ADDMC. And this one when we added ADDMC. So you see that it improves it in a significant way. So it was an important addition to the portfolio. But then Jeff Dudek realized, he said, wait a minute, what you really want to do is 3D composition, right? I said, yeah, but it's hard. He said, well, there are good solvers out there. Let's go back. Let's go to the competition. Let's use a good 3D composers and see whether we can go back to the original idea, which was using 3D composition to optimize conjunctive queries. And that we were able to do this in a follow-up paper. And we built another solver, which was DMPC. Actually, DPMC, it's a typo. Dynamic Programming Model Counting. And again, we were able to take the portfolio we had before, and that was the VBS with all the a whole bunch of solver, including ADDMC. And again, we added DPMC, and we see a significant improvement. So let me kind of conclude now. I try to give you the concept of logical algorithmics, and we showed that it gives rise to descriptive complexity theory and to multivariate complexity theory. And we get beautiful theory for CSP, for dichotomy result. And we actually get a very practical approach today for quantitative Boolean reasoning. In fact, not only for quantitative, just a couple of weeks ago, I was at CAV, and I had a paper with students on using, again, 3D composition for Boolean synthesis. So this is, it is not competitive or just sheer SAT solving, but when you look at richer problem, it's become an important technique to use the perspective we got from logical algorithmic with the new tool today that we have good tool for 3D composition. Thank you very much.
We can take a few questions. Okay.
So what happened to descriptive complexity?
It's a little bit like the theory, which is the sense that you have a beautiful theory, and there are very important problems, and the important problems seem to be beyond our reach. So the same way you ask, what happened to complexity theory? And answer, the big problems we still are not able to solve. And the question today I think we have to ask about this is, does the theory offer insight for the practice? And in classical complexity theory, I think there is a growing gap. You look today and say, how much complexity theory help us understand what happened in practice? The answer is less and less. If you take here, if you include here, which is part of descriptive complexity theory, which looking at remember, descriptive complexity theory look at syntax as a resource. So the number of variables is a resource. So in that case, here, descriptive complexity theory, this focus on number of variables, did give us a guideline that led us to this tool. These tools are inspired by the perspective of descriptive complexity theory. Says, if you can minimize the syntax, you reduce the practical complexity. So this bridge that I would say for standard complex theory has been missing. Here, actually, I see a better bridge between the theory and the practice.
Moshe, yeah, thanks for the very nice talk.
Hold it closer to your mouth.
Sorry. Yeah, thanks for the very nice talk. Just a quick comment about this the question about descriptive complexity. It is a fact that while we do not have a logic for polynomial time for unordered structures, if you do restrict the class of structures, for example, to graphs of boundary width,
If we do what?
if we do restrict the class of structures to, for example, graphs of boundary width or even generally relation structures of boundary width, FPC does characterize polynomial time.
Yes, yes,
Yes.
So, for example, again, what we know now that on many problems that are hard become easy on bounded tree width structures, and in fact, the algorithm are going to be very often a fixed point will capture polynomial time on bounded tree width structures. So again, you get insight on descriptive complexity theory that are relevant to the practice. Here.
Yeah, go ahead.
Yeah. So this aspect of restricting the variables, which is like restricting the syntax somewhat, in Cygus solvers. So Cygus synthesis problem is expresses some quantifying, solving some quantified alternation, trying to find some expressions, and they do use restrictions on the syntax of the expressions that.
Which solvers?
Cygus, this
Yes.
synthesis
So
solvers. Now, can this be?
Yes.
That's an extension of, it's a restriction on syntax. They count the number of operators, variables, and then find a thing. If this line of research can be applied there.
Look, I mean, even if you want, one of the big success in formal methods has been bounded model checking. And if people have done the same in planning, it's a bounded planning. So the problem is hard. Let's just find a parameter, important parameter, and let's fix the parameter and see how much we can do. So today, if you look at the practice of model checking, for example, most common technique is bounded model checking. Yes, it does not give us the full answer, but give us interesting answers. And that technique, Cygus essentially says, we're trying to solve some synthesis problem. Let's solve bounded synthesis problem. Essentially, they're saying, let's take, instead of searching for a program, we'll do something, let's check for a program of bounded size. Even for reactive synthesis, there is also what people call bounded synthesis. Let's limit the number of states in the strategy and things like that. So yes, this is I call it the strategy of you can run longer if you run slower. Okay, when you run a marathon, you don't run a marathon like you run a 100-meter dash, right? You have to discipline yourself. I need to run 42 kilometers, okay? I need to have a speed that I can take for 42 kilometers, so you can run longer. So we start with ambitious program we want to solve, and we say, oh, that's going to be too hard. Let's be more modest. What can we do? I remember when model checking idea was floated in the 80s, the people who did horse-style verification said, finite state programs. Who care about finite state programs? You should do what we do, okay? Full-fledged programs, okay? And you have to give credit to like Ed Clark, who was not intimidated. He used to do horse-style verification. He said, no, bounded number of, finite number of states is important. Let's do it. And now we say bounded number of states is important. What can we do with that?
Okay, so I think in the interests of time, let's thank Moshe for the wonderful talk. And so Moshe, there is a memento for you. And I guess the protocol is you'll have to open it and show it.
See the composition inside.
Bounded number of people to. Okay, so there's coffee and snacks outside, and Yeah, we reconvene back at 10:30, but the chair and the speakers for the next session, please stay back so that we can.
Okay, again, I'm here to announce that please follow TCS security protocols. Please do not bring any food and beverages inside the MPH. There are whiteboard and markers placed at various places. Please feel free to contact the volunteers. Thank you.
Thanks for your time. Yes, that would be.
Time.
Does it work? Don't work. Okay.
Hello, hello.
French ear, I think that I have. Yes, yes, yes.
No, I think.
That doesn't work. Yeah.
Kanta? Mic test, mic test. Hello, hello. Hello, hello, hello. Ah. Hello, 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 hello. Volume commission. कम है volume. बहुत कम है.
Hello, 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 hello.
Increase कर.
लगाते कैसे मेरे को यही क्लियर मैं बोल रहा हूँ भाई।
हेलो 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 हेलो
नहीं सीधा देख।
हेलो हेलो Am I the first one?
ऐसे लगाते कैसे हैं, एक बार बताना।
इसे लगोगे ना तो इसे लॉक करने का,
अच्छा ऐसा।
और फिर इसको ऐसा ऐसा ले सकते हैं यहाँ पे नजदीक। इस साइड भी लगा सकते हैं, इस साइड भी लगा सकते
हाँ वो बट इस साइड बेंट है ऑलरेडी।
Oh, that screen is great.
हैं again.
Yeah, because in my talks on Tuesday, I didn't have. Yes, yes. Can you hear me? Is it fine? Yeah. Has to be closer to the mouth. Yeah. Yeah. Okay. Good. Good. Excellent.
बस अब तो और चेंज इंक्रीज। This is the first one. It's fine. We just will put it in order.
Hello, hello, hello.
पिंच करत नाही ना. चेक टेस्ट 1 2 3 4 चेक टेस्ट टेस्ट टेस्ट. हेलो 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 चेक चेक चेक. हेलो 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 हेलो.
अभी करता हूँ। वो क्या ही शायद करते करते अगर इधर चला जाता है। हाँ तो फिर वो इधर आते हैं, इधर आता है तो फिर एक इधर आ जाता है। क्या करूँगा, या तो ये तरीका है कि मैं डुप्लीकेट करूँगी। साइड आ जा रहा है वो तो मैं समझ गया था कि इसमें तो अपन कुछ में क्या हुआ अगर जैसे कर्सर आइसक्रीम पे लिया है तो फिर वो एडिट करने के लिए कुछ डुप्लीकेट में ये लैपटॉप की स्क्रीन अगर मान लो कुछ एडिट के लिए तो आप लोग हमिंग हमिंग अच्छा लेवल हमने कम करके रखा है। ऑफ करके तो बैकअप के लिए